All right, hi everyone. Welcome to the first recitation session of the summer. What we're going to do today is we're going to do a quick recap of some of the main things that we talked about during Dr. Roberts' first two lectures on Monday and Tuesday, so yesterday and the day before. And we pretty much have covered the first four sections of pardon me, of chapter 12. So just going through what some of that stuff looked like. So the main thing that we did in chapter 12, so we started off with section 12.1. And what we looked at here, a couple of things we looked at. This is mostly in coordinates in three-dimensional space. So if you take points, let's call these points, P is going to be X, Y, Z, and Q is, it's supposed to be a Q, A, B, C. Well, if you have those, sorry, one second. Trying to move some of my control panels a little bit. So if you have all that, then the distance from your point P to your point Q, we write this as the distance from P to Q is PQ with these little bars around it. And that's just the square root of X minus A squared plus Y minus B squared plus Z minus C squared. And that's the distance. And by the way, if you stare at that for a second, you might say, well, wait a minute, that looks an awful lot like something else that we looked at. So this is one thing that we talked about in section 12.1. Here's the other thing that we talked about in section 12.1 is on spheres. Right? So a sphere that has center given by A, B, C, and a radius R, well, then the equation of that sphere is going to be X minus A squared plus Y minus B squared plus Z minus C squared is equal to R squared. And we should be comparing this formula for the sphere with the formula for distance between 2 points. Because what is a sphere? A sphere is, strictly speaking, if you really want to be technical about this, a sphere is the set of all points. So the sphere is, in other words, the set of points actually, let me be a little more specific with that. It's a set of points which we usually write as X, Y, Z. That are distance R from the center ABC. And when you think about it that way, then you'll realize, oh, well, of course the sphere has to be of this form because that's just the distance squared, and that equals R squared, which is obviously the square of the distance. So so those are the same thing. Now I want to do some examples of this, looking at some particular kinds of spheres. There's also a weed whacker behind me, so I apologize if there's a buzz in the background. I tried closing all the doors, but it only goes so far, it seems. I'm also, let me just see, is there a, by the way, so if anyone has any questions about anything at any point, you can type them into the chat window and then I will answer them. So the example that I want to look at basically is to consider the sphere. And here's the sphere. The sphere that I want to look at is is given by x squared plus y squared plus z squared minus 2x minus 4y plus 8z is equal to 15. And my claim is that this is an equation of a sphere. That's what I claim. So the problem here is to find the center and radius. And you may look at that and you'll say, well, I don't believe that's a sphere for a second. That looks nothing like the sphere equation. Yeah, that's true, but the idea here is we're going to get it to look like a sphere. So here's the strategy we're going to use. So the gist basically is we're going to say, so the solution of this is we want it to look like our sphere equation that we're used to, right? X minus a squared plus y minus b squared plus z minus c squared, right? Equals r squared. Now, I don't know what a, b, and c are, and I don't know what r is either, but I know that I want that equation to look like that. And as soon as it does, then we'll know immediately what the center and radius are. So how are we going to do that? Well, basically, we're going to use a classical strategy from high school algebra known as completing the square. So just to remind everyone about what that looks like, so I'll just do a little side review in a different color here. So recall completing the square. And basically, the idea here is as soon as you write something like x plus a, big A, not to be confused with that little a, x plus a squared is equal to x squared plus 2ax plus a squared. So we're going to look at and I'm running out of space already. Can I scroll this, I wonder? Is it possible to do that? No, I guess not. But I can make another whiteboard. Okay, great. So so what we're going to do, that's the idea, is to complete the square. So in this case, what do we have? We have we have that x squared minus 2x, I don't know what comes next, I'm going to leave that blank, plus y squared minus 4y, I don't know what that is, I'm going to leave that blank, plus z squared plus 8z, I don't know what that is, I'm going to leave that blank, equals 15, and a whole bunch of stuff on the other side of it. I'm actually going to go over to the next slide so I can write this all again. So this is the same exact problem as before. So we've got x squared plus 2x, I'm going to leave that blank, plus y squared, was it plus x or, no, it was minus 2x, excuse me. Excuse me, I wrote the wrong sign there. Y squared minus 4y, going to leave that blank, plus z squared plus 8z, I don't know what comes next, I'm going to leave that blank, equals 15. Now what we want, now this is what we have, right? And we haven't done anything so far. All we've done is we've just rearranged the terms of it, so we've grouped all the x's together and all of the y's together. That's the only thing that we've done so far. But what do we want? What we want is for this to look like x minus a squared plus y minus b squared plus z minus c squared equals, uh, 15. equals r squared. And I don't know what a, b, and c, and r are. I don't know what any of those things are, but we're going to find out. So x minus a squared, if you undo that, completing the square, that would give us, in that case, that would be x squared minus 2ax plus a squared plus y squared minus 2by plus b squared plus z squared minus 2cz plus z squared, oh, excuse me, plus c squared equals r squared, after you expand all that. Now let's compare these things. We know, for example, that we have, we know, for example, that we've got the x squared minus 2x, that's one item, x squared minus 2ax. Oh, well, what's a in that case? You compare these two objects, we find that a has to be equal to 1, because, and why is that? Well, that's because we need -2 to be equal to -2a, right? That's coming from the x terms. These things have to be the same, right? These, the whole point is that these two equations have to be equal to each other. So x squared minus 2x, x squared minus 2ax, a is 1. So, well, we don't have a 1, so what are we going to do? Well, we're going to add a 1 in on that side. Now we've changed the story, right? Now we've broken the rules. We've added something to one side. So the golden rule of mathematics is do unto one side what you do unto the other. So as soon as we add 1 to one side, we have to turn it into the other side as well. So 15 plus 1. Same story with the y and the z terms. So for the y terms, we can see in this case that y squared minus 2by plus b squared. In this case, b is going to be 2. We see that. Y squared minus 4y. So b squared, we're going to add a 4 on that. So because b squared is then 4 plus 4. And then 8z, in this case, that tells us that c is going to be equal to -4, right? So it's plus 8z, but c is -4 in that case, because you need -2c is equal to, and again, why is that? That's because -2c has to be equal to 8. The only way that can happen is if c is -4. So c squared is 16. You're going to add a 16 to that side. Okay, so we've done all of that. And now that we've done all that, where does that leave us? Well, we end up with the x minus 1 squared plus y minus 2 squared plus z plus 4. It's a plus 4 in this case because we found that it's going to be c minus 4, but we want it to be z minus c, minus -4. So it's going to be plus 4 in that case. And now you just add all of them up. 15 plus 1 plus 4, or in other words, 20 plus 16 is 36 on that side. That's our sphere equation. Now, the original problem, just to refresh our memory, the original problem was to find the center and radius of that sphere. 37. Did I? 16 plus 4 is 20. 20 plus 16 is 36. I think that I'm right about this. Yeah. So the people math wrong sometimes. So and it is entirely possible for me to make mistakes as well. So please do make sure that I'm doing things right as I'm doing this. Thank you for keeping me honest. So, but the good news is that as we're at this point, what does that give us? That tells us that the center, we can see at this point what the center is. The center is ABC, which tells us the center is the point 1 to -4. And the radius is 6, the square root of what's on the right-hand side. So there's the solution to our problem. Very good. Now, one second. I am. Okay, so that's one example. Let's do another one. Let's look at another way of doing this. Suppose we have. Suppose we want to. Oh, sorry, hold on. So suppose we have, as our next example, we have 2x squared plus 2y squared plus 2z squared is equal to 8x minus 24z plus 1. And it looks a little scary in this case because you've got these extra terms in there. That's no problem. You can just divide everything by 2. That's not going to cause any problems at all. So in other words, that's just going to give us x squared minus 4x after dividing everything by 2 and moving the terms over, plus y squared. Now there are no y terms over there, so you can leave that as it is, plus z squared plus 12z, you can leave that blank again, is equal to, in this case, it's going to be 1/2. So what do we add in? Well, let's look at what happens with the x terms. So the x terms we have, again, same thing as before, negative 2a is equal to negative 4, so a is equal to 2, which means that a squared is going to be 4, so we're going to add in a 4 on that side. Meanwhile, we also have, now there are no y terms, so we can, in other words, we can see basically that negative 2b is equal to 0, basically. So b is just 0. There's no issue there. We can leave y as it is. And then that leaves us with c, with the z terms. And we see in this case the negative 2c is equal to 12, which tells us that c is going to be equal to negative 6. So we're going to add a term of 36 onto that side. And again, do unto one side what you do unto the other. Plus 4 plus 36. So having done all of that, that gives us x squared minus 4x plus 4. So what is that? That's going to be x minus 2 squared plus y squared plus z plus 6 squared is equal to 40 plus 1/2, or 81 over 2. And so what that tells us is that the center, what do we think the center is? Well, the first coordinate is 2. The last coordinate is negative 6. The middle coordinate is going to be 0. Y isn't, nothing's being subtracted from y, so it's going to be 2, 0, negative 6. And the radius is 9 over root 2. Taking the square root of that whole thing. All right, questions so far? Okay, so now, what if we let's try something else. What if we went on to do what if we went on to do something else? What if we wanted to talk about, here's a new kind of problem, which is to find the equation of a sphere whose center is, excuse me, not whose center. Let me, that's not what I wanted to say. I wanted to say with the endpoints, sorry, here's some endpoints. Let me try, I wrote this badly on my notes. The equation of the sphere with one diameter having endpoints. That's what I wanted to say. Having the endpoints 5, 4, 3. And 1, 6, negative 9. What does that mean? Well, what we should be imagining in this case is we've got our sphere, right? And it's got some center. We're going to find that center. But it also has a, we've also got, a diameter that's going through it. And that diameter in one of these, lines that's going through it, one of these points is going to be the point 5, 4, 3. And the other point is going to be the point 1, 6, negative 9. Obviously, this here is not to scale, but that's not important. So the question we should be asking ourselves is, okay, well, how are we going to find the center and the radius? That's really what we need, right? So we need, in this case, is the center and the radius. That's what we need in this case. So if we're using the center and the radius to find that, well, what do we know? Well, the radius is going to be what? The radius is going to be 1/2 of the diameter, right? Radius is 1/2 the length of diameter. And what that means, what that's going to mean in this case, is that the length of the diameter is the distance between these 2 points. So in other words, it's the square root of 5 minus 1 squared plus 4 minus 3 squared plus 3 plus 9 squared, right? Or in other words, the square root of 4 squared plus 1 plus 12 squared, or 144 plus 6. So we can calculate the distance between points as we would with vectors. Yes, absolutely. So the so great question. So in other words, this just wrapping this up, 16 plus 144 plus 1, it should come out to 160, square root of 161 in that case. Yes, absolutely. So the question is, can we calculate distance between points as we would with vectors? Absolutely. So for example, let me just do that as an aside for a second. Let's say that we've got the points. P is going to be x1, y1, z1. And let's say that Q is the point x2, y2, z2. Often we'll write the vector between them the vector that's between P and Q is often written as PQ with a little vector over it, which we can write as what? That's just going to be x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. And the distance between, and so the length of the vector is the exact same thing as the distance between the points. I mean, you can see that immediately in both cases, they're going to be the square root of, now if you're looking at the distance between points, x2 minus x1, y2 minus y1, z2 minus z1, square each of them, take the square root. But the magnitude of the vector, on the other hand, it's just the exact same thing, only in that case, it's going to be coordinates, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Same exact thing in both cases. So yes, the distance between points and the magnitude of a vector, it's basically the same exact thing. Also, how did you get 4 minus 3 for the middle term in the distance? By flipping a number that I shouldn't have. That is an honest mistake on my part. So that should not be 4 minus 3. That should be 4 minus 6. Because I saw the 4 and the 3 next to each other in that point, and that was my bad. So that changes the story a little bit. Thank you for catching that. 4 minus 6 squared should be plus 2 squared. So 16 plus 4 is, this will make a little bit more sense. 16 plus 4 is 20, plus 144 is 164 in that case. Good? So that tells us what the radius is. We now need to know the center. The center is the midpoint. And the midpoint between two points, so the midpoint formula, you can write that as just the average of the 2 points, x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. That's the midpoint. The midpoint between 2 points is just the average of all of the coordinates. In this case, what would that be? In our case, that would be x1 plus x2, 5 plus 1 over 2. 4 plus 6 over 2. 3 minus 9 over 2. Or in other words, the point 3, 3, 5, 3 minus 9 is negative 6 over 2, so negative 3. So all of which is to say that this point, the center of our sphere, comes out to be 3, 5, negative 3. Now we know this. So the equation we want is going to be x minus 3 squared plus y minus 5 squared plus z plus 3 squared is equal to 164. Good? Questions? Okay, so now spheres, etc., that's a lot of the analytic geometry of coordinates. What we also care about are, as we've mentioned, vectors. So let's talk about some important vector properties that we consider. So vectors, I'm going to write these properties in 2 dimensions, but they work just as well in 3 dimensions. So let's say you've got one vector v, which I'm going to call AB, and w, which I'm going to call CD. And again, I'm doing this in 2 dimensions for brevity, but it works just as well in 3 dimensions. We remember some properties here, right? We can talk about vector addition, easy enough. V plus W is A plus C, comma, B plus D. And that's the algebraic approach, but it's important, by the way, to remember what this means geometrically as well. So if here's our vector V, and here's our vector W, well, this right here, this next one that I'm drawing, is also the vector W, right? Those are the same thing. We consider vectors to only be an arrow. We don't consider them to be, in particular, we don't consider them to be to be dependent on where they start. Just the just the direction and the length that they're going in, which means in particular that this W, let me get a little laser pointer here, this W and this W are exactly the same thing for our purposes. And the vector between them is V plus W, that's horribly drawn, which is just tail to tip. That's the gist here. That the vector between them is V plus W. So that's addition. We also have scalar multiplication, which we've seen. Let's say that you've got, I don't know, I'm going to call it alpha. Like alpha is some real number. And what does that mean? That means that alpha V is equal to alpha A, alpha B. And again, if this is our vector V, then that same vector, but elongated, that's trying to be the same vector in the same direction, maybe alpha V, right? Scaled by a factor of alpha. Or you could have it going in the opposite direction. You can also have these vectors going opposite, alpha V, if alpha is a negative number, in which case they go in the opposite direction. The upshot of this, by the way, an important consequence of all of this is that V and W are parallel. V and W are parallel vectors only when, or precisely when, I'll say, precisely if V is equal to alpha W for some alpha, i.e. what that is to say is that V and W are scalar multiples. Another very important principle that we have here is we've already talked about this a little bit. We can talk about the magnitude of a vector. The magnitude of a vector, again, using the same notation as I did above, that's just the square root of a squared plus b squared, the length in 2 dimensions. Or you can do all of these things in 3 dimensions, by the way. The formulas are exactly analogous. So if you, for example, have that V is ABC, then we have that V is the square root of a squared plus b squared plus c squared, right? By the way, this is one thing that I like doing is pointing out common mistakes. Here's a mistake that if you haven't seen this before, it's tempting to say, oh, well, you're adding vectors, you add them coordinate-wise. You take a scalar multiple, you take them, you just multiply each number by that scalar. You take the absolute value of the vector, you just take the absolute value of each of the coordinates. That is not true. That last one is not the case. Do not do this. Do not write the following, that if you have the magnitude of V, that is not the same thing. That is absolutely not the same thing as doing the vector of magnitude A, magnitude B, magnitude C. It is not the same thing as taking the absolute value of each of those coordinates themselves. It means something completely different. It means the total length of the vector. And this just gives you a vector of positive numbers, and a length cannot be a vector. A length is a number, length. I mean, just like in the English word length, it's a number. So don't do that. Now, but when we can talk about scalar multiples and we can talk about lengths, then we can introduce another important concept, which is about something called a unit vector. What's a unit vector? A unit vector is a very special kind of vector, and what's special about a unit vector is a vector with length 1. That's all. That's all it means. Now, there are a few important examples of this. For example, the coordinate unit vectors are I, 1, 0, 0, J, which is 0, 1, 0, K, which is 0, 0, 1. Those are all examples of unit vectors, but they're not the only ones. There are lots and lots and lots and lots of other unit vectors. So, you know, here's another example of a unit vector. You could take the vector u, I'll make something up. You can take the vector negative 1 over root 2, 1 over root 2, 0. That's a unit vector. That is a unit vector. Its length is 1. If you take its length, the magnitude of u, in that case, is just the square root of 1/2 plus 1/2 plus 0. And that's 1. The length of that vector is 1. So that's a unit vector. No question about that. Now, an important property of length, by the way, so useful property of magnitude if you take some number alpha, right, or yeah, I'll call it alpha again. If alpha is a scalar, i.e. a real number, then what do you know about the length of alpha times v? Well, let's think about what v is again, right? Here's v, and then you can take alpha v, right? You've multiplied the length by alpha, and this is what happens if alpha is a positive number. But you could also have it be the case that alpha is a negative number, in which case you'd be going in the opposite direction. So if alpha is a scalar, then what that tells us is that the magnitude of alpha v is the magnitude of alpha, or the absolute value of alpha, times the magnitude of the vector v. And that's very useful for us. It turns out that's a very useful property. And I'll tell you why that's a very useful property. What that tells you in particular, so if v, I'm just going to give you some random v, right? So if v is a vector, then the unit vector in the direction of v is given by what? The unit vector in the direction of v is no more, no less than v multiplied by 1 over its own magnitude. Sometimes you see this written as v over magnitude v. And if you're not convinced that's a unit vector, then just apply this property. What that tells you in particular is that the magnitude of 1 over the magnitude of v times v is the same thing as 1 over the magnitude of v, because that's a positive number, times v. Well, that's very obviously 1. Just cancel the 1 over v in that case. So unit vectors are very important, and they're, a common misunderstanding is that, oh, the unit vectors are I, j, and k, and no other vectors are unit vectors. But that is not true. There are lots of other unit vectors like this u that I made up over here. This u is equal to negative 1 over root 2, 1 over root 2, 0. That's also a unit vector, even though it's not one of the coordinate unit vectors. So here's an example. Here's a very common type of problem that you may consider. And it's actually quite practical in lots of different science and engineering applications. Suppose we have a vector. Let's say that the vector v, I'm going to call this vector v, and the vector is going to be the vector 6, 2, negative 3. All right, and it's and I want a vector with the same length sorry, I want a vector not the same length. Excuse me. The same direction. And length 4. So a good place to start here, is by making v a unit vector. And why is that a good starting place? That's a great starting place because as soon as v is a unit vector, you can do pretty much whatever you want with it. You want to scale it, you want to flip it, do whatever you want. It's very easy to get a vector of a desired length if you're starting with a unit vector. Just multiply it by whatever length you want. So let's start by making it a unit vector, and if we do that, then we need to know the magnitude of v. Magnitude of v in this case is what? 6 squared, so it's 36, plus 4 squared, so 2 squared, so plus 4, plus negative 3 squared, so plus 9, or in other words, root 49, or in other words, 7. So that's a vector with, so the length of v is 7. We know that to begin with. So the unit vector in the direction of v is 1 over 7 times this vector, 6 to negative 3. That's a unit vector. Now we can take it a step further now and say that, okay, well, we want it to be a length of 4. So we're starting off with some vector v of length 7. We turned it, this is very much not to scale, but we turned it into a unit vector of length 1. And now we're going to take that unit vector, multiply it by a factor of 4 to get a unit vector with length 4. Again, this is very much not to scale. I'm sorry about that, but I only have a limited amount of board space I can work with. And so how do we do that? I'll just multiply the unit vector by 4. So the vector we want is 4 over 7 times 6 to negative 3. Now, if this were an in-person class, then it would be perfectly fine to leave your vector in this form, and you have to be comfortable with seeing vectors in this form. There's nothing wrong with this. Do you have to multiply that into the entire vector? No, you don't have to, but there's nothing wrong with doing that, though. You can leave it as that. You can also leave it as 24 over 7, comma 8 over 7, comma negative 12 over 7. Both of those are fine, but you may see them on, because this is an online class and there will be multiple choice questions. You have to get used to seeing things in both of these forms. These are unequivocally the same thing. So it's important to get used to seeing things in that form. Okay. What else? So questions on this problem. All right. So we also looked at dot products, right? This was section 12.3. Dot products. And basically what a dot product is, if you take your vectors, let's give these vectors new names. Let's call this A is going to be A1, A2, A3. Oh, by the way, maybe I should mention this also. You could also write this as A1I plus A2J plus A3K. There's absolutely nothing wrong with doing that. Those are both perfectly the same thing. I'll tell you what's not the same thing, though. This is not the same thing. It is not the same thing to write this as A1I plus A2J, A2J, comma, A3K. That's not the same thing. I mean, I know that as soon as you get used to this kind of new notation, it's like, ooh, we're using angular brackets. Oh, we got to use like I, J hat, K hat, and cool things like that. So, it's very tempting. It's always very cool notation we get to use, and it's very tempting to try to just throw it all in once. But no, this is nonsense. This is a nonsense statement at this point because that's a vector that contains other vectors, and that makes no sense. So the important thing is just leave this as either A1, A2, A3 in that order triple with the angular brackets, or as A1I plus A2J plus A3K. Either of those is fine, but you really do have to choose one of those two forms of notation. Anyways, let's say that B is going to be B1, B2, B3, or if you prefer, B1I plus B2J plus B3K. And what can we do at this point? We can say then that a dot B, the dot product between the two of them, is going to be A1, B1 plus A2, B2 plus A3, B3. Notice this is a scalar, right? Joe likes to call this the half-assed dot product. When we, this is not the same thing again as saying A1, B1, comma, A2, B2, comma, A3, B3, comma. That's not what we're doing. We're not getting a vector out of this. You can multiply vectors together to get another vector. That's called a cross product, and we'll talk about that in a little bit. But that's not how we do it. And I'm not saying that you're not allowed to do this. I'm not saying that you can't invent an operation between vectors that does this. What I'm saying is that in the past 300, 400 years of vector analysis and three-dimensional analytic geometry, the human race has never found a useful application of this operation. So we just don't do it. It's just not useful for us. Now, with all this in mind, so you take these dot products. So here's another thing that we sometimes see. Let's say, for example, that A is going to be the vector. A is going to be the vector negative I plus 4J plus 8K. And B is going to be the vector 12I plus J plus 2K. Is the dot product also called scalar projection? No, it is not. The scalar projection is a different thing. We'll talk about that in just a second. They are very closely related, but no, the dot product is not also called scalar projection. It is sometimes called a scalar product, however. So the dot product is sometimes, so the dot product is the same thing as saying scalar product. but it's not the same thing as saying scalar projection. That's a slightly different, it's a slightly different notion, which we'll talk about that, and we'll talk about that in a little bit. So hold on to your hats. So the I wanted to point out though, if you tried doing this dot product, A dot B, here's a common mistake. Here's a common mistake that we see when people try to use IJK notation, is that they'll write this thing, and this is not true, but every now and then we'll see this. They'll try writing this as oh, well, just follow this formula, right? You're just going to multiply the top two things together. So negative I times 12I, so that's negative 12I plus 4j times j. Okay, that's just 4 times 1, so 4j, 8 times 2 plus 16k. But no, that's not right, because that is, again, this not real dot product, right? That's the fake dot product. So that's not correct. That's still a vector, right? Even though you're not using the angular brackets, that's a vector. And I don't want that to be a vector. Because the dot product is called scalar product, that should really be a scalar. So actually, let's try that again. A dot B actually is going to be negative 12 plus 4 plus 16, or in other words, 8. That's your final answer. In that case, you take the dot product, you get a scalar. But let's talk about scalar projection for a second. So with scalar projection, now we've got these two other operations that come out of this. So scalar projection of A onto B. Now, of A, right? The key phrase here is of A and onto B. The way that we write this is comp B A. If you want, you can also write this as comp B parentheses A. There's nothing wrong with doing that. And this actually is a little bit advantageous, because you think of, for example, you compare this to the phrase f of x, right? That's the same thing as saying f of x, like so. So of A, right? So we're saying of A. A is what's going inside of it. Onto B, right? A is going onto B. B is, i.e. B is below. It's under, right? It's onto the thing that's below. So comp A onto B, comp of A onto B. So, and likewise with scalar projection, same issue. So comp A, what's the formula here? The formula of scalar projection, the formula here is going to be comp BA is, now you do take a dot product. As I said, these things are related, but you divide it through by the magnitude of B. This is the formula for the scalar component of A onto B. What does this actually represent? Well, let's say that we take two vectors. Let's say that here's A, and here's B. Actually, I'm gonna reverse those. I'm going to say that this, yeah, that's actually not going to give the figure that I want. Let me try that again. So this is going to be B, and this is going to be A in this case. And the figure that we have in mind here when we do this, the comp AB, what that actually is, you drop a perpendicular line, and what that gives you, having done this, is a new vector, right? The new vector that we get right? We get this new vector underneath it, right? And the length of that vector new vector is the magnitude of the scalar component. Right? That's the power behind that. The magnitude of the scalar component gives you the absolute value of the scalar component, I should say, gives you this distance in that figure. Closely related to this, well, what about actually finding that vector itself? The vector itself is the vector projection right? The vector projection of A, again, same nomenclature, of A onto B. And with that in mind, we can work this out. This is sometimes called proj BA. Sometimes, by the way, sometimes this is just called projection without specifying vector. In this class, when we say vector projection, we'll say vector projection. If we want a vector projection, we're going to say vector projection specifically. And likewise, when we want a scalar projection, we'll say scalar projection. But in general, outside of this class, if you have to deal with projections at some point, which you may, then sometimes they'll just call this the projection. They won't specify scalar or vector. But if they don't specify, that usually just means vector. And what that actually is just A dot B over the magnitude of B squared, right? Just the dot product of B with itself times B. A bit of a clunkier formula in some ways, but essentially what it comes down to is the vector in either in the same or opposite direction as B, the length is given by the magnitude of comp A onto B. And it's the same direction if A dot B is positive, and the opposite direction if A dot B is negative. All right? So that's what scalar and vector projections are. I guess I should actually, before I go on to my next slide, I should point out that that in this particular case, in the figure that I've drawn here, this pink vector, this actually is proj A onto B, is what that pink vector actually is. Its length is the magnitude of the scalar projection. Okay. So now the last thing that I wanted to talk about today, I know that I'm going a bit over than I expected to. I'm sorry about that. But the last thing I wanted to talk about today was this is section 12.4 on cross products. All right, for cross products, what is this? This is the, usually we'll write this as A cross B. Now this is only for three-dimensional vectors. Right? This is the rare case where you can only do this in the case of three-dimensional vectors. And in that case, what does this come out to? I, j, k. And you've got A1, A2, A3, B1, B2, B3. And I never actually memorized the explicit formula going outward because it's just too clunky, too much stuff to memorize. But this, for me, is very easy to remember. So this is always what I will fall back on. So if you want to do a concrete example of something like this, you can take A to be, I don't know, -1, 1, 2, and you can take B to be 2, 1, 4. And if that's the case, then A cross B is I, J, K. 1, 2, 3. Oh, sorry, I read the wrong vector. My bad. -1, 1, 2, 2, 1, 4. And if you do this out, what does that become? 1 times 4, so 4, minus 2, right? So that's going to be, so what is that? That's going to be 1 times 4 minus 2 times 1. Right? That's the first term. Meanwhile, you're going to take minus, oh, sorry, that's I. That's the I term. Minus J is going to be -4 minus 2, right? And what's that coming from? That's coming from the, sorry, -4, excuse me. I wrote that wrong. Let me fix that. See, I math wrong too sometimes. So, and that's just coming from the 1 times 4, -1 times 4, and the -2 times, and the 2 times 2. You always, by the way, you always subtract the middle term. Right? Easy to forget this, but always subtract the middle term there. J. Plus, and finally, for the k term, we're going to get -1 minus 2, k. And that right there is just coming from the 1 times 1 and minus 1 times 2. So all of this together, and that's so just to clean everything up, that's that term, and then there's the last term there. So I'm trying to color code what we're doing here. So the so having done all of that, this finally comes out to 2i plus 8j, because it's -4 minus 4 times -1, minus 3k. By the way, what's an important property of cross products? The most important property of cross products. The most important property of cross products is, this is the important fact, the whole purpose behind these things, which is that A cross B is orthogonal to A, and also A cross B is orthogonal to B. I should have mentioned this before. What that means in particular is A cross B dotted with A is 0, and also A cross B dotted with B is 0, since vectors V and W are orthogonal if and only if their dot product is 0. Important fact about dot products, which I should have mentioned before. This is very good for us because this is very good for us. I tried a different method with the I and j vectors on the side, and my j vector came out as 8 instead of negative. Well, that's good that your vector came out as positive 8 because my vector came out as positive 8 for the j term as well. So I think we're on the same page. Negative instead of 8. Well, let's see what happened. Let's test this for a second. Because the good news is you can always check your cross products. So in our example, we can always check this because we've got that A is -1, 1, 2. So A dotted with what we think is A cross B. What does that come out to? That comes out to -1, 1, 2, dotted with 2, 8, -3, which gives us -2 plus 8 minus 6, and that's 0, so that's good. That's good. What about the other one? We also have B dot A cross B. And in that case, that's going to be 2, 1, 4, dotted with 2, 8, -3. And what does that come out to? 4 plus 8 minus 12, and that's also 0. So that also works. So if you got -8 for your j term instead of 8, probably you forgot to flip a sign somewhere. Probably if you put the I and j vectors on, if you rearranged them, if you rearranged the vectors, then probably that would explain why you got a different number. Because if you flip the columns and you play around with that too much, then often that can result in signs getting flipped. So check your signs in that case. Yeah. Okay, sure, no problem. So so that's the cross product. A couple important, and by the way, just to reiterate what I just said, you can always do this. You can always check your cross products. And cross products, let's face it, they're a bit of a messy and complicated thing to calculate. And it's very, 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 very easy to make a mistake doing them. Happens literally all the time. The good news is they're very easy to check because you can always check to make sure that they're orthogonal to both of your vectors. And if they're not, something went wrong. So they're very good. The nice thing about cross products is it's very easy to check them. And the other important thing about cross products is that they have a lot of nice geometric properties. So for example, so some geometric facts about cross products. One of them, we already mentioned this, but A cross B, the vector you get from that, is orthogonal to both the vector A and the vector B. Important, probably the most important property about cross products, but there are other very useful ones as well. For example, the parallelogram formed by A and B has area given by the magnitude of A cross B, the magnitude of that thing. So in particular, you can say here's your A and here's your B. As a result, you're going to get this parallelogram that comes from completing both sides of it. The area is, the area of that thing is magnitude A cross B. What if you wanted to complete it in the other direction, though? What if, for example, you said, I don't know, let's say, well, that's really the best way to do it is to Can you do it another way? I guess you can't really, because if you the whole point is you position the vectors so that that was I see. I was getting that confused with something else. I'll come back to that in a little bit. But the other third fact here is the area of the volume of the parallelepiped formed by your vectors A, B, and C has, so is, I already completed that sentence, is given by, you can write this in a couple different ways. You can write this as the absolute value of A dot B cross C. It's known as the scalar triple product. But it turns out that that's the same exact thing as the absolute value of the following determinant: A1, A2, A3, B1, B2, B3, C1, C2, C3. Turns out that's the exact same formula in that case. And I'm putting double bars around it because I'm indicating it's the absolute value of this determinant, not just the determinant itself. And the figure we should have in our minds as we're looking at that is something like, here's your A, and here's B, and maybe here's C going into the background there. And you can complete A and C in this way if I'm a remotely good artist, which I'm not, but bear with me. The resulting parallelepiped with these three vectors, A, B, and C, has volume given by this formula. That's one of the most important facts about cross products as well. I want to return for a little bit, though, to this parallelogram issue. So a common problem that we'll often see with this, and this is the last thing that I'll do today, a common thing that we see with this is that the area is, we can look at the area of the triangle PQR, where I'm going to say P is the point 1, 0, 1. Q is the point -2, 1, 3. And R is the point 4, 2, 5. All right. Now the strategy. The strategy here is going to be to write this as PQ. It's 1/2 times the area of the parallelogram formed by PQ and QR, right? So if you've got your point P, you've got your point Q, and you've got your point R. You've got PQ, and you've got, you've got PQ, and you've got QR, like so. Well, the area that we're interested in is this, right? So PQ cross QR, I'll rewrite QR in that case. QR is, again, just down here, right? That's QR, right there. And we can see that it is indeed 1/2 of, and here's PQ. So here's P and Q and R, and if we're focusing really on these two vectors with their tails touching, right, then the resulting parallelogram that we get, we can still cut that in half and get the area that we're really interested in, PQR. Or, same figure, in this case, PQR. Again, we're trying to find the area of this triangle, doing my best to make it the same triangle. But you want to do PQ and then PR. If you do PQ, so this is PQ cross QR, or 1/2 PQ cross QR. If you do it in this case, well, then here's PQ again, and here's PR. I just wrote the same thing twice. Oopsie. PQ cross PR. And now you have a triangle with this parallelogram, but once again, it's going to be the exact same area that we're interested in. Right? Where in this case, we're focusing on these two triangles with their tails attached. So it doesn't matter in particular. So what's the point? The point is it doesn't matter which which of the three vectors, which combination of the three vectors you want to use. They're all going to be the same. 1/2 PQ cross QR, 1/2 PQ cross PR, 1/2 PR cross PQ. You can sorry, PR cross not PQ. I already did that one. Cross QR. You can do so. You can go from PR to QR, right? That would be these two, right? So that would be PQ cross QR. And it all ends up being the same exact thing, right? So PQ and QR. Once again, you get half of this area, but then these two triangles are just the same exact triangle. So it really doesn't matter which ones you use. It'll all come out to be the same area no matter what. I know that there are a few people who are wondering about this in the previous lecture. So in this case, what do we have? Well, let's just do the first one because why not? PQ, we can see what that's going to be. -2 minus 1, that's -3. 1 minus 0, that's 1. 3 minus 1 is going to be 2. That's your vector PQ. And QR, right? The vector QR in this case is going to be 4 minus -2, or 6. 2 minus 1 is 1. 5 minus 3 is 2. So there's our vectors PQ and QR. Just double check that's right. -2 minus 1 is 3. 1 minus 0 is 1. 3 minus 1 is 2. 4 minus -2 is 6. 2 minus 1 is 1. 5 minus 3 is 2. Always check yourself before you wreck yourself. And what that means is PQ cross QR. You take your cross product, IJK. -3, 1, 2. 6, 1, 2. Cross it. I turns out to what? 1. So 2 minus 2. I is going to be 0, right? So it's 0i. J minus -6 minus 12. So minus -6 minus 12. J plus -3 minus 6 K. Or in other words, what is that? 18J minus 9K, right? And if you try this, we see, yeah, that's going to be orthogonal because to test this, so just to check, in both cases we get 18 plus 2 times -9 is in fact 0 in both cases. So yeah, you take the dot product of PQ and PQ cross QR and QR dot PQ cross QR, you get 0 in both cases. So yeah, we did this right. We can do a little trick here though. Here's the trick. The trick is that's the same thing as 9 times the vector 0 to -1. Right? All I did was factor out a 9. That's going to help us. That's going to help us, and it's going to make our calculations a little bit easier because from there, what can we say? what we can say then is that 1/2 times the magnitude of PQ cross QR, well, that magnitude is going to be 1/2 times the magnitude of 9 times the vector 0, 2, -1, right? Or 9/2 times the magnitude of 0, 2, -1, which just makes our lives a little bit easier. I'm going to continue this on up here, which basically gives us 9/2 times the square root of 4 plus 1, or in other words, 9/2 root 5. That is the area of this triangle, 9/2 root 5. All right. So that's just the same thing that we were doing before. So it's a little trick here, right? The trick that I did was, taking advantage. The trick to make our lives easier is to factor out a common multiple, right? Or take out a factor out a common factor to make the magnitude easier. Does it matter which vectors you cross? Like if you use PR rather than QR, would the answer be yes? That was my point with this. Yes, it would be the same. That was my point with these figures. If you chose to do PQ and QR or PQ and PR, this blue thing over here is what you get when you do PQ, right? Here's PQ, and here's QR. And those vectors give you the same triangle, right? That's a parallelogram, and that gives you this triangle. On the other hand, you can do PQ and PR down here, cross those things, that gives you this parallelogram, and that gives you this triangle. Or you can do PR and QR over here and here, and that gives you this parallelogram, but that still gives you the same area for the same triangle as before. So yes, it doesn't matter. Any combination you do, it will be the same. Yeah, no problem. So the and if you want, you can always, just to further check your work. I mean, you can switch out the PQ for the PR, and it will give you the same area. You can check that. You can check it yourself. It'll give you the same area. So, all right, that's all I have to talk about today. So the plan is for tomorrow, not tomorrow. Well, tomorrow is your guided study group, and you can use the same Zoom room to do that. And then on Friday, what I'm going to do is I'm going to post some challenging problems to look at. They're not going to be collected. You don't have to scan them or do anything, but we do encourage you to do them. They will help you very much with your studying and with your understanding of the material. And we're going to talk about those challenge problems on Friday to sort of prime you for thinking about what all this geometry is for going forward. Thank you, and I will talk to you guys on Friday. Good luck, everyone.